Scientists have finally figured out how Roman concrete was made. The Pantheon, which is still intact 2,000 years after it was built, still holds the record for the world's largest dome of unreinforced concrete. It struck me very early on that Roman concrete was just different to everything else. I mean, look at this thing. If I didn't know any better, you could tell me that this was 50 or 100 years old, and I'd be like, yeah, that seems about right for the amount of wear and tear compared to the other buildings around where I live. Except that's 2,000 years old. But that's not even the most impressive part. You see, when Roman concrete cracks, it actually has the ability to heal and strengthen itself, completely healing those cracks on its own as if it was some kind of living, regenerative being. What? Side note, like, how many times have you driven through a city where there's like maintenance being happening on a bridge that's like 20 years old? This thing's 2,000 years old. It's still standing up. Like, what is going on here? Anyway, this is a point that has frustrated me since I was quite young, like 13 or 14 or 15, because nobody actually knew how they did this. So about 10 years ago, scientists declared that they'd finally solved the mystery, and I was really excited by this, but they said that it was the volcanic ash that the Romans added to the concrete, which reacted with water to strengthen and heal the cracks in the concrete. But the mechanism for how exactly this worked wasn't described in the paper, and it just felt a bit empty to me. Like, it seemed like we were on the right track, but it wasn't the full story. Well, hold on to your panties, because as of 2 days ago, we finally know. So this is the paper behind me, and you should check this out because it's a brilliant paper. And basically the team said that the ingredients are really important, but there is a smoking gun. These small white chunks of what they call relic limestone stand out in the concrete because everything else in the concrete is extremely well mixed. I mean, there's a big chunk of lava there, but for the most part, this is extremely well mixed and meticulously made. And previously, these had just been thought to have been like the result of poor mixing, but this didn't really sit right with the researchers given how meticulously everything else was done. So the team took 10 samples of Roman concrete from the city wall of Privernum, an archaeological site which is near Rome, and then they fired a scanning electron microscope with an attachment called an energy dispersive spectroscopy. Now basically this just blasts the samples with electrons, which causes X-rays to come flying off, and when you measure those X-rays, they tell you exactly what is in the chemical composition of the sample. It's pretty cool stuff. I've used something very similar called X-ray fluorescence before, which does the same thing. It's a very useful tool that we use a lot. Anyway, back to these big red things which are lime chunks. Now basically, the experiment showed that the particular lime reaction that occurs in Roman concrete can only occur at really high temperatures. And this high temperature mixing, which we don't do, we mix it cold, also adds a bunch of chemical reactions that are not present otherwise. But here's where it gets crazy. So the big lime chunks are actually the largest particles in the concrete matrix, and they have the highest surface area. And the team noticed that the cracks almost always formed along where the lime particles were because of this, which causes the limestone to be exposed to the elements. And when water flows over the cracks when it's raining or it's flooding, the lime reacts with the water to form a hard calcium carbonate, essentially gluing the crack back together. This can happen in as little time as 2 weeks, and it's why Roman concrete lasts forever, especially if it's in the water. I am shooketh.